what I wanted to at least start to talk about is the why do we even want the rocket stove? I mean, what's the benefit? Mainly, it's beyond the original use of it in the house, where we're not emitting smoke into the house. It basically is a really efficient use of firewood. So we're consuming a lot less wood than we would in a normal cast iron wood stove of the same heat output, for example. As I said, the efficiency on these units is about 90%. People in northern climates even have gone through, say, 1 cord of wood in a compact home or a small home. 1 cord of wood in where their neighbors may go through 7 or 8. So it's that much different. I mean, it really burns. You don't burn it 12 hours straight. I mean, generally 4 hours, 3-4 hours to maybe 6 hours maximum is enough to charge that cob completely to where it's full of heat, and then it starts to ooze heat. But there's no real point in continually burning the fire if you've already charged the mass unit into its full charge. So the heat will go through an inch of cob in about an hour. So it takes that long to start driving the heat from the ductwork out through the cob. So you may have 4 to 5 inches of cob or 6 inches of cob around the tubes. So that means 6 inches of cob is 6 hours by the time the outside of that becomes warm. So it does take a while to charge. But in the meantime, you've got the bell or the barrel radiating heat, so you're not uncomfortable after lighting the stove. It takes a little while for that barrel to get hot, but that barrel will get, as I said, somewhere between 200 degrees and as high as 700 or 750 degrees. So that's, at the height of its burn. Yeah.
So I know that on a daily basis, then overnight, like say you burned it for 2 or 3 hours, and then you've left it and come back to it the next day, is it still going to be at about like 70 degrees?
Yeah. The discussion I had earlier about trouble starting it and getting the flow right and all that, that generally almost always happens. Well, it can happen on windy days. Sometimes a windy day will actually just like even a fireplace will do that. A windy day may push the air backwards and you get a puff of smoke in your face. So a windy day can be a problem. But mainly it's a cold start that's a problem. But once your heating season starts, just like anybody who uses any fireplace, wood stove, barrel stove, any kind of wood burning appliance, cook stove, once you start in October or November, you're going to be doing it till March or February. It's always going to be a warm startup, is what I'm saying, which I think is what you're asking. I mean, you basically get up in the morning and you're going to say burn it for 3 hours, let's say, just say, and then you stop it, and then maybe in the evening, after supper or before supper or whatever, around that period of time, you maybe charge it again and do a couple hours, and then you go to bed. So you might be sort of charging it before you go to sleep, but then you're not going to be getting up. You don't need to. You charge it, and then it's going to flame through, and it's going to just pack that thing with heat all while you're sleeping, and then in the morning, the fire has been out for hours, but the heat is just going to keep on oozing off that thing, and when you go to start your morning fire again, it's going to just want to go the right direction.
I've seen designs that people had like double beds, like laid out on it.
Yeah. Oh yeah. There's all sorts of. They're not soft. I mean, it's you can feel the cob, but you have to put, you put some cotton padding. Some. It's not hot that it's going to burn anything. It's very warm. It's like a heating pad. Yeah. And you can get enough loft in a cotton layered, like a futon cover, a futon mattress, which generally, not the really, really thick ones, but there's some smaller, thinner ones that's just sort of layered cotton or wool or whatever, and you can lay that down and it's comfortable. In fact, actually it's better for your back to have a firm mattress. And then the heat will just come right up. And then in the daytime, you can just sit on it, sit on the bare thing, or just put a little cushion on there and pillows, and it's very comfortable.
So you're talking about a cord of wood, but does the wood have to be broken down, like split more?
Yes, that's the other part. When I said dry, I did mention it has to be dry. It also is much more beneficial if you cut it into smaller pieces and not really long pieces. You don't really, 18 inches is even too long. 16, 15, something like that is about the right length. And smaller kindling, you can forage from the woods exactly the kind of fuel you need. You just take a bundle under your arm, that's your day's fuel. That's your whole 24 hours of fuel, just a 5-minute walk. I mean, not every piece of wood you're going to pick up is going to be dry enough, especially if it's been raining beforehand. But if you go out on a day when you've had several days of sun and you just walk around the woods, you're going to be able to get a lot of firewood of the size. I'm talking about limbs that are, that kind of size. A log that size you might want to chop into like eighths. But other than that, you can just go out in the woods and just get oak and dried pine or whatever that is dry and cut it to that length, and that's
What
fine.
diameter would you be talking about?
Whatever that would be. An inch would be good, and 2 inches would be about max, I guess. 2.5.
So what about things that are flammable, like walnut hulls?
They'll probably be okay, but I wouldn't put a large percentage of the full mix of them because they'll tend to pile up. You don't want it to build up a pile of them that don't burn. Because the sticks self-feed. A walnut hull doesn't self-feed, it just sits at the bottom.
Yeah.
That's the problem. I mean, you can mix them in.
So I guess there was one picture of the pots that sit down in, but it didn't have a barrel. If you were to have the barrel situation and your cooktop would be less efficient, I guess, because you'd just be heating the bottom of the pot as opposed to the sides as well. In that situation, is there any other way to integrate the cooking, like dropping it down right on top of the firebox as opposed to setting it on top of the barrel? What would make sense?
I think what you could do there is keep the height of the barrel, keep the top of the barrel at the 2-inch height above the heat riser, like we normally would in building it. And then you could build your cob up around the barrel and come in, fold it in, and make a smaller circle on the lid of that barrel, and then put your pots in there. What you'd have to do then is then you would have to settle for a shorter riser and then a shorter feed tube. Although there's a ratio, which I probably should tell you now. The ratio of feed tube to horizontal tube, fire tunnel to heat riser is, in a very basic sense, is 1 to 2 to 4. So 12 inches to 24 inches to 48 inches. Okay, and the more scientific numbers would be 1 to 1.5 to 3.5. So that's 12 inches to 18 inches to 40 inches, 42 inches.
So I guess what would the feasibility be of if you had a cooking stove that was more practical for cooking and with an oven and stuff, and connecting that somehow so that the excess heat that's coming off that fairly inefficient stove is going into the cob, and then it can still radiate out when you're not solely lighting the heat.
You could have your traditional J-shaped combustion unit and your barrel, so you get heat for your radiance. Comes out of the barrel, and then your cooking surface is down where you could actually get to it, say 3 feet or whatever of tubing, of ducting is where the cooking surface is going to be, and then it goes right out the flue. That way it's going to come out plenty hot from the barrel, hot enough to cook and everything, and then you design your heating bench or your cooking bench at that point, right there at 3 foot.
When you're considering your ratios, do you also have to consider where your wood comes out, or does your wood come out in a certain spot?
Where it comes out of the barrel, that's not part of the 3 parts, but that part has to be actually bigger than the rest of it, because it tends to gather. If ash is going to gather any place, it's going to be a lot of it right in the bottom of the feed tube, but it also tends to gather at the base of that exit from the barrel or the bell, which is called the manifold. And while we're on the numbers, I might as well just tell you that the 8-inch tube, which we're using, is essentially roughly 50 square inches of cross-sectional area. So you've got a 8-inch tube, and you've got, say, an 8-inch by 8-inch square. This is 8 inches across, so the radius is 4 inches, so it's pi r squared. 4 times 4 equals 16 times 3.14. So in this case, as I said, the 8-inch tube is 50.24 square inches of area. We got our 8-inch square, and that's going to be 8 by 8, of course, is 64. So let me make sure that 8 by 8 is 64 if I remember. So that's 64. So if you transit from the whole key of this thing, really, the whole key of the rocket stove, this is another figures example, is to try to maintain the same CSA, the same cross-sectional area from the very opening part to the end of to the beginning of the manifold, and continuing on through the duct work itself.
Isn't that a reason why that has to be a rocket line above the machine?
Exactly. Very specific sizing of everything on the way through, height-wise, width-wise, and depth-wise in the sense of the tunnel. That's why the opening, the feed tube opening, in the very beginning here in the front where you put the wood is not 8 inches. So you have an 8-inch round, roughly 50 square inches. The reason I don't have an 8-inch square to feed the tubes is because that's 64 square inches. I want 50. So to make 50, the unit size I chose is 7.5 wide by 7 inches deep and 7 inches tall. 7 inches wide and 7 inches across, but then when you go horizontal, it turns into 7 inches tall. 7.25 times 7 is about 52 square inches. So, it's very close. It doesn't have to be perfect, but it's very close. So that's why we maintain that all the way through. But what I was saying, at the manifold part, when it goes into the barrel, that changes because there's a lot more area. It's probably 3 times more. All of a sudden, it gets bigger. But that's okay because it has to go somewhere, and it gets sent right back through into its normal 50 again as it goes through all these incarnations of twists and turns. What we want to do is make that exit area from the bell to the entrance of these ducts big enough that in case we don't want to be collecting a lot of ash and residue in there. We give it enough room to build up to some extent, give it a little leeway there. So if it does build up a little bit before you get a chance to clean it out, it'll still flow unimpeded. And since we already have a fairly large expansion as it goes through the barrel, the bell, and all that, it doesn't really matter that much at that point. But again, it's coming in at 50 and it's going out at 50. So that's really what matters. You can't fool around too much with those numbers.
Not mentioned the air inlet size.
Right here?
Yeah.
7.
Is there a ratio there that's important? And when you say 200 degrees or 400 degrees, are you talking Fahrenheit or Celsius?
Fahrenheit. So that's that. The first question is there a ratio for the size of the opening? Yes, and that ratio is that we are trying to get 50 square inches of opening through the exit flue and through the entrance. So that where you put the wood is going to be 7.5 inches by 7 inches. If you used a 6-inch pipe instead of an 8-inch pipe, that would be about 30 or 35 square inches. So then you'd have to make that feed tube that much smaller. And you can figure that out. That might be 6 inches by 6.25.
What the air inlet?
Well, the air inlet is this part.
It comes down from the top?
Yes, it comes down from the top.
The diagrams show an air tube.
If you don't use a lid, which is really not that common, lids aren't usually people don't use lids. If you don't use a lid, it's 7.5 inches wide by 7 inches deep, and that is your air inlet. If you do have a lid on it, then you have to have an air inlet from the end, and that's really more for control and smoke control. But if you design the stove right, you won't need that.
So where your manifold, on the design that you have here, the manifold is at the same level of where your horizontal burn is. Does that make a difference as to where your manifold is?
The manifold the barrel is going to rest on the course of brick that I have laid out here. It's generally it's a brick thick, or in this case I put 2 split bricks. It's going to rest on that, so your manifold occurs right above that point at the very bottom. One barrel is too short. You have to have, in this design, you have to have one and a third barrel approximately. We're going to have to cut the second barrel, and that'll be the base which gets set, and we have to calculate how deep that cut barrel is to get the top of the upper barrel to the right height above the heat riser. So that's a little tricky, but that's how it's done. The other thing I want to say is that if you stuck a ruler right now into this thing to say measure the height of our heat tunnel, it's about 6 3/4 inches tall. The roof of that heat tunnel is about 6 3/4 inches tall. It's not 7. By the time we finish laying this up, because of the mortar joints, it's going to have a little mortar joint under it. So it's going to pick, we have 1, we have 2, we have 3, 4. It's going to pick them up to the point where we will have a 7-inch tunnel by the time we're finished. This is not traditional bricklaying. This is not mortar like we would use in a chimney or a outdoor barbecue or a brick wall or whatever. This is basically, the mortar is meant mainly to level and to seal joints between the bricks. It's not really a glue. The weight of the bricks being stacked up and the pressure or the continuity of all that cob mass around the unit is what's sealing and holding everything together, really. What I'm calling mortar, which is not like our regular mason's mortar, is really just a leveling device and a seal. So it's really different than a bricklayer's experience. Yeah.
You may have already covered this. I think I might not have tracked completely, but instead of using the larger pipes, would it not make sense to use smaller and then make more runs so that you have more surface area to?
If that was the case, then using our formula here, your feed tube would have to be, how much wood could you get in that little hole? That's one reason why that's not working. The other thing is it really doesn't flow that well. Below a certain size, which is about 6 inches, it doesn't really flow that well over long distances. When it's natural gas and you're using a 3 or 4 inch exit off your hot water heater, it's fine because it's a whole different gas. It's hotter. It's a straight run. It's all that. So basically, everything I'm talking about is going to be 8, but I could be doing this whole discussion on a 6 as well. I just don't want to confuse people because the numbers for the 6 are different than the 8. The books have, the calculations for the different sizes, but.
So I guess with this though, is just to use this. So instead of using an 8, if you had used 6, instead of having 2 pass, you had 3 pass.
Instead of trying to make up your heat by putting more passes in, your best choice would be to use an 8-inch pipe. If you use a 6-inch pipe, you're going to be building a smaller stove and getting less heat out of it. That's all. That's the way to think of it. That's why in the beginning of the handout I said this kind of a stove is a totally different way of thinking about how you're used to heating and whatever. Basically just living with less heat. You're maybe having a 35,000 or 30,000 BTU unit instead of a 52,000 BTU unit. 8-inch, over 50,000. 6-inch, a little over 30,000. That's how we're looking at it. Just like when you're buying a wood stove. I mean, the little baby Yodel, little teeny baby one, the parlor stove only puts out, 24,000 BTU, but the big mama bear puts out, 76, and that's just the difference. What I do want to do is make sure I show you the patterns and the methodology and the important stuff like the insulation, the ducting, and this stacking of the combustion unit. But this is important. If you look at this wall here, this is what it looked like before. Essentially, they had some Tyvek or some kind of a wind barrier. It's just on the back side of the facing board of the sheathing on the outside, which is just like that. It's just board and batten. From a fire standpoint, that is totally unacceptable for a stove of any kind. The second thing, the wind infiltration through here is crazy. So, way, way too much. So there's no point in building this thing unless we're just going to use it for a little cook stove or just to sit on. If there was wind blowing through here and, it just couldn't, we have to stop some of that infiltration to some extent. What I've done here from a fire standpoint mainly is that this stuff here was left over, this part of our scrounge stuff was left over from another project we had where we had to insulate a building fairly tightly. This is an extruded polystyrene It's not blue board. It's not what most people use in insulation. It's a cheaper insulation in a normal residential application. Is what they call blue board. That's an expanded polystyrene. This is the same basic material, but it's processed in a totally different way. It's extruded. It's actually pushed through a machine under pressure, and it is much denser, totally waterproof, and it has a fairly high flame resistance. It's not fireproof by any means, but it has a fairly decent flame resistance. I don't know what that is. I mean, I should know, but I believe it's maybe 400 or something like that. It's a little more expensive, but it's really a good product. This particular one happened to be 2 inches. You can get it 1 inch, ½ inch, I think 3/4, 2 inch, and I think that's about it. So I basically cut every little square in here. It's easy to cut with a knife or a saw. Actually, I used the drywall saw. And just cut between the rafters and the battens, which are the cross pieces here. Just squished it in there between. You can see what I've done up at the top where I've left it exposed on purpose so you can see it. Really doesn't take that long. You just push it in there. Even if it's not perfect, there's always a seam around the edges. I mean, there's always going to be a little bit of a draft around the edges, but then we use this other stuff. This is a mineral wool, a spun mineral wool. Has an incredibly high, like 20, some of them are between 18 and 22,200 degrees Fahrenheit flammability rating. It's a very dense product. It's not itchy. It's not like fiber. It looks like fiberglass, but it doesn't. There's no itch to it. So it's fireproof. It's a little bit more water resistant. It's 50 square feet is about $40, so it's not cheap, but purely for the fire resistance and the sealing against any cracks I may have left in the boards and stuff, this was a really good choice. So we're cutting this stuff and just jamming it in. You can pass it around if you want. I got that at Lowe's. It's called Roxel. That's not the only brand name, but it's just called Roxel. Rockwool, Roxel, there's other names for it. Just for the fire resistance, it's just a piece of this cement board. It's just a fiber cement board. It's usually used in bathtub surrounds. Tile backing is what it is. It's waterproof. It's totally flammable proof. Tile is a good heat mass. So that's important. On the floor here, same deal. We've got a whole unit here that's going to be just oozing with heat. We want that heat migrating into the masonry mass here. The bricks, the rubble. When you go to the brickyard or to the cement place or whatever, the block place, Lowe's even if they have damage, they always have broken block, broken cement. People bust up sidewalks, and this rubble can be thrown in and among as you're packing the cob, you can be packing the rubble. It could be brick, it could be concrete, it could be stone, broken up stone, whatever. We'll be packing that in among the masonry so we have a good mass heat sink. All that heat is going to absorb into this. A brick does not have the heat storage capacity of a piece of concrete, so try to put more concrete in. What we want is, more heat storage. So I'll be junking in a lot of this stuff. What we don't want is that heat oozing into this knee wall, or particularly into the floor, heating up this floor, because it's just going to go out here and just dissipate. So what I've done is we've insulated with a cement board, insulated underneath this base pad, so there's a thermal block between the warm stove unit and the floor. And then these are scraps left over from the same stuff as that, left over from another project. Yeah, we don't want the heat as well going into that knee wall because that's exposed to the outside, on the outside. So there is a expansion joint underneath here separating the floor from the little wall, because any heat that might get into the floor there is not going to want to get out. But we can't just have the heated cob right up against that. So we'll put some of this insulation here, and it'll be all covered up. But that's going to be a thermal break, so it can't go beyond that. It's going to stay within its own little unit here. So that's important. Yeah.
Did you see any advantages to do for like a radiant floor heating to wrap PEX around the tubes as they're coming through to have a little water pump the water through?
That would work, but then you're not going to get. First of all, it would probably impede the draft In other words, you'd be removing so much heat from the ductwork that you wouldn't have enough to continue the flow. It's basically an engine. You're sucking air through the air filter at this end, and you're exhausting it out the tailpipe up there. And if you steal so much heat from the system towards the end, it's going to stop the flow.
Depending on how much water, what speed the water circulates.
Oh, sure.
The perlite is going to be stealing the heat also, right? It's just not as much.
Well, if you take hot water, you're not going to get the mass hot enough. That's one thing. And if you take hot water, you may impede the flow of. You may cool it down to the point where you're impeding the flow of flue gases, which would be a real problem. Not having as much mass heated would be okay because you're getting hot water heated. So that's.
Well, my thought with the hot water is the actual radiant floor. So instead of having one heat source here, the heat's more evenly distributed.
I guess what I'm saying is you're not going to be able to do both. It's okay to pull the heat off no more than you would, than the cob would pull the heat off for water, if that makes sense, as long as you don't start pulling so much off that you're taking so much heat out that it's going to, especially in the sort of the front of the system, at this point where it's starting its way through the path, that you're going to steal so much heat that the exhaust can't flow. But yes, you're stealing heat. The whole idea of the stove is that you are stealing heat from that duct as you're burning. And so if you replace the cob with spiral pipe and devote it to water heating the slab, that's okay, but it can't be too much. Yeah.
Would you be able, on top of the bell, stick another water drum and maybe run PEX or something like that through that and use it as a heat exchanger and draw water up heat without a problem?
You could do that. That's what that guy was doing with the stainless steel in the UK, that one. That's essentially what he's doing. However, if you steal, at any point, if you take enough heat out of the system in the middle of its operation, it's going to affect how much heat is going downstream. And if it immediately didn't affect the actual flow of gases, you would be taking water and living with less mass heat. If you took too much heat for the water and too much heat for the mass, you at some point you're going to stop the flow of gases because you're taking away too much of the heat. However, by the time in a normally operating system, by the time it comes out the exit flue, at that point, it's already lost most of its heat anyway. So it's not like it can't be cool at the end, but it just can't be interrupted in the middle with a massive reduction of heat all of a sudden. But I think a small amount of water circulating, or a pot or whatever on the surface, or a drum that would be circulating water for heating in a reasonable amount of volume would be okay on the bell. Yeah.
I'm wondering if people wanted that, they could do a design where there was like an insulating thing that kept the heat from hitting the water where you had the water jacket until the stove was going big time, the house was nice and warm, and then you just pull that apart and let it throw heat there before you stop running it.
You can do that, but then you have to refire the stove, and you can actually run a rocket stove and feed it enough wood that you're replicating as if you were living with a regular wood stove. If you want to go that far and do what you're saying, then that's fine. Most people are going to use the rocket stove as the initial incarnation was to reduce emissions drastically. I mean, 90%, if not more. And number two, to use a whole lot less wood. You can feed all the wood you want into it. If you have a place to store that extra heat, like you just said, and you don't mind using more wood, yes, that'd be fine. It's just that you'll be physically feeding it more to do that. And some of the point is that you really don't have to babysit it too much. Generally, these stoves will be run 3 to 4 hours a day, and they burn through all their stuff, and then that's the end of it. Or then maybe another scenario might be 3 or 4 hours a day in the morning, and then you're doing your job in the daytime, and then say it's around supper time, and then it's still very warm. The stove's oozing heat, and it's still warm. It's easy to start a second burn, another 2, 3, 4 hours for the evening, and then you go to bed. Your fire's long gone. By the time you go ready to bed, it's already burned out, but it's still making heat. So your total burn for the day is 6 hours or so. So that's
So you might decide I'm going to do 8 hours and I can heat my hot water that way.
Right, exactly. Yeah, if you want to do that,
If you only heat your hot water in the wintertime, that way you sure would do it in the summer.
No, No. In fact, these stoves don't work, as I pointed out in the beginning, before we had the PowerPoint, these stoves really don't work that well in the summer. I mean, for a little heating unit like the Lorena stove, they do, because there's not that long, tortuous path on the way out. But these stoves generally work best in a cold, where your winter season is longer and colder, and where you don't have a lot of time in the interim seasons, like where the fall and the winter and the fall and the spring are shorter. It works out pretty good because they're short seasons. But if you have an extended spring and an extended fall, that sometimes makes a problem, because with the inside of the house is colder than the outside. That's when your reversal of flow wants to be the problem. And the way we resolve that is to put those primer holes, as I explained before, at the right point in the system, so that we train it, force it in the very beginning to start going the right direction, and then once the real flame starts, it'll go that way.
So what do you think the maximum outdoor temperature that this works effectively at is?
Well, it depends. It's totally dependent on the height, all that formula of the height and how big the stove is. But I mean, you start getting into, like even today in the beginning, and it's mainly because, I built a little quickie burnable one out there. Was it 75 degrees maybe at that point? It was having trouble, but that was a cold start. I had to really start a little fire and shove it with a stick back well into the burn tunnel and make it, and block the entrance and make it go out. And once that started to flow, after several attempts, it did. That's because it's sort of warm today.
There'd be no problem with 40s and 50s.
No, that would be fine unless, well, 40 would be fine. 45, yeah, 50 maybe. That's the cusp. I mean, it just depends on how cold it was in the building. Because if it's cold, really cold in the building, let's say you weren't living in it and you came back from 2 weeks someplace else and then it was cold in the building, that might be a bad day.
So if you put the board insulation underneath your slab, that just becomes part of the stove and part of the thermal mass, right?
That actually insulates between, that board is serving as insulation.
Right, what I'm saying is, in not this scenario, if you put your board underneath before the slab is poured, then that becomes part of the thermal mass. That would be an ideal scenario, right? Because even with the concrete board, it's still going to lose some into the ground.
Yeah, it's not a very effective insulation. This board isn't very effective, but it's something. If it was a wooden floor, or if I wanted to be a lot more efficient about how this was, what we would do here, maybe still use the concrete board, but I would also build a little wall around out of concrete block or bricks around that pad, and then I would mix perlite, which is an insulation material in that bag, mix perlite and clay and make a insulative mud. And then build 3 inches of that, approximately, it could be 2 inches or 3 inches. Level that, and then put that brick pad on top of that.
So you think that would be better to put under a concrete slab than the blue board?
If you're building a house from scratch, let's just use it because it's so much easier, and you want to have a warm floor, yes, you always have to have insulation underneath the full slab, and especially around the perimeter. You really can't put it under the slab once the slab's poured. So if you knew your house had that, then you don't want to put blue board, you want to put extruded polystyrene. Really be very specific when you buy it. It has to say XPS on it. And it'll have it's not all made by Dow, and this stuff isn't made by Dow either. But it'll have a R rating on there, and it's usually 5 per inch. So, that's pretty decent. Some of the blue board, the cheaper blue board is only like 4.2 or something like that.
So like the ISO boards, which are even higher than that, aren't as good for that application, though?
This stuff is a very high compression rate. So like the radiant floor heat concrete pour we did for the soldier fly house, that's a fairly heavy thing. Well, underneath the floor is 2 inches of this, and it would take a lot more weight before that would crush. I mean, I don't know the number, but it's an extremely high crush rating on this stuff. The blue board does not have that rating at all, so that's not, even if it was insulated, okay, if you stacked 4 of them on there, once you start that concrete pour on there, it would crush it and make it uneven, basically. So it's XPS.
So if you had a wooden floor, you put this stuff down, the concrete board or whatever it is, and then do your thing with the perlite and clays.
Yeah.
3 inches.
3 inches.
Level it out.
And level it out.
Let it dry
And then put the brick on top. Well, no, that's it. I mean, the perlite and the clay is a good, cheap way to do it. The other thing which I have to mention, which I have said before, if everybody didn't hear it, is that if you have a crawl space or a basement, this is a 5,000 pounds and up, and some of these units are 12,000 pounds. I mean, if you make it a really big one, you have to get under, and most likely, and without an engineer's approval on it, if you're not going to go that far, but most likely you're going to have to put piers. They don't have to be fancy, just steel jacks or concrete posts or something, or treated wood or something, has to be put under each joist in several places around under there, because the floor just won't take it. You got 5,000 pounds over so many square feet, and you can figure out how many pounds per square foot. Most floors are rated residentially at 60 pounds per square foot. Some other ones, some less used ones where the people aren't gathering, like bedrooms or something, might only be 40. Something like this may be 100. I mean, that's way beyond the limit. So, and engineers will design over limit. I mean, but not, you don't want to push that number too much. So you really have to get under there and make sure that it's jacked up. Let's get up and I'll show you this, this part here, so we know what we're doing. We've dedicated a space to our stove. On this side, I was limited by the wall. It's a flammable wall, dry oak, terrible wall to put next to it, but we completely seal that with cement board. By the time the heat gets to that end of the unit, it's really not going to be all that hot. It's all going to be absorbed into the mass. And that, as I said, that thing is going to be probably about 200 degrees, and that's going to be a good 16 or 18 inches away from the wood there. So I'm not worried about that. This side, we don't want Marshall rolling over one end of our stove with his John Deere. So we're probably going to end that about here. I left 5-6 inches there for the terminus of this side. I was aiming for about 4.5 feet. It's probably going to be finished about 5 feet out. I really didn't want to go out too far, but I have to have something. So this tubes, you can't have these close together. The design, the way they do these elbows and stuff, makes it so it's really very difficult, if not impossible, to get them too close together, because you don't want sharp bends. You want these sweeps. These are as sharp as you want. Sort of a rounded bend. So you want very little constriction in the pipe, and of course these have to be a little bit wrinkly, because that's how you get your angles. By turning those things, the angles will adjust from 22 degrees to 90 degrees, depending on how the direction of each of these is being turned. So the distance here, between here, you want like a minimum of about 5 inches. And this is about 6. At that end, it might be 8 or more. So we're fine there. So the main thing to do is to make sure we have enough space and we're sort of in the right spot to get that end here where the barrel is going to be, where that's going to join the barrel. And we know where the barrel is going to be because the front of that thing is going to be right there. We really don't know where there is. We don't, because I didn't know. I just know we're going to use this space, but I do know where a chimney is. So we have to sort of work backwards from that, assemble this, and see. And we can cut that and we can cut that, but we have to know how wide we're going to be, and then we also have to know this way how much leeway we have for cutting. So we stick that up under there, and there's an elbow somewhere here that is the other part of this, that it goes with another right angle, and once that's all attached, then we know where this is going to end, and we can do a proper trim. So that barrel is going to be right about at that point. Yeah, let me see that. So that is essentially going to hook onto that. There's another piece of stovepipe, but it's going to be cut, and so it'll be about that high, something like that. And this will be up at an angle. As we set these up on bricks, yeah, you can hold it up. Let's see. Thank you. So this is it. We'll just take this, jam it up here, but that's I think it's a little too long, so we'll probably have to trim that. But essentially, this last piece is going to be a very visible upslope, which is actually a good thing. But we don't want it too upslopey, because I really don't, for aesthetic purposes, I don't want it exposed. I want everything vertical to be the only thing exposed. Everything else I want buried in mud. The other thing is too, the deeper that gets buried in mud, the more mass there is to absorb the heat. But by the time it comes to this last part, there really isn't a whole lot of heat, but it's still hot. I mean, still, you're not going to be able to put your hand on it. It's going to be in the, in the mud. So the very important point here is to keep the slope or angle of exit always upward. It doesn't have to be a whole lot. A pitch, it can be just a little like a plumbing pitch, just a slight one. But it always has to be going up. So if this starts at, say, 4 inches above the ground, that one needs to be like at 5, and then this one has to be at 6 or 7, and then this one, of course, is going to be whatever it needs to be to allow it to go upward but not be exposed. So that is going to be the more drastic upward incline. But what we're doing is adjusting this so that once these are all connected, we know where the pipe's going to end, and that's where we're going to put this pad. And we know that combustion unit is centered on this pad, so you measure from the front of that to the line here, and then I know where I'm going to put the barrel, because I know that the barrel is going to be about 12 inches, 11 and a half inches is going to be the center point of that exit flue stack there, or that heat riser. So I can do it like this. When I said 11 and a half, 12 inches, I know that because the barrel is about 23 inches circumference. So you take that 23, and half of that is 11 and a half. And so I got my 11 and a half or 12-inch point. Doesn't have to be perfect, but we know that the whole unit here is about 36 inches. And so I just transfer that 36 to here. And that's where I'm going to put the combustion unit and the front of this pad. So we know this way how much I have to go because I've already done this, and I know this way how much I know because I've got enough metal to cut either from here or there to make this way correct.
So you got the barrel coming down here. This is now about here.
Yes.
The barrel over top of it. The heat coming back down. How do you get that heat into that tube?
The barrel will rest on this. Okay? It's going to be,
This thing right
yeah, that's going to be, I can fill that with brick, I can cut little pieces of brick, or I can just stuff mud in there. But this is going to be the resting place of the bottom of our barrel unit.
So you have to notch the barrel?
Yes, then we have to take a metal saw and cut the barrel. This is fairly smooth. We're going to cut the barrel here and here and then down again, and then it goes around. So there's going to be a big square hole. We're trying to avoid cutting it like the side. We really don't want to start cutting steps, just make a straight cut. If we make a mistake, or if the bricks don't fit right or whatever, we can always jam stove gasket in there. This is a wood stove door gasket. It's a high temperature gasket. We can jam it into the crack, and then all that stuff will be sealed with mud anyway, so it doesn't matter. The barrel comes here like this, so we're just going to cut a hole at any point along this back side. It could come off the side, be an angle cut and come off like a I don't know how to describe it. A miter, yeah. We could do it that way, or make it simple, which is the way we sort of planned it. It's just cut a hole here, bend the cut tabs every inch or inch and a half around the thing, and just fold them open. One goes in, one goes out, or just however, and we sheet metal screw or rivet the end of the pipe into the side of that barrel and do it that way. And then everything's going to be sealed with cob, so any leaks, really don't want leaks, but if there were any leaks, they would be a non-issue because there's 5 inches of mud around everything, and that stuff will harden with the heat, so it's not going to go anyplace. Now, if it did crack, which can happen, if it did crack, it's not going to shoot flame. I mean, at this point, most likely it's not going to be shooting flame out of this. But if it did crack all the way down to the metal, if the mortar wasn't mixed correctly, or if it was just a physical problem with the floor or something, you'd probably have a smoke leak at that point. Then you would have to fix it. You'd have to repair it. Repairing this is not a big deal. It's just chisel it out and just put more in there.
What is the life of a barrel?
Well, I said at
This is a standard barrel?
it's a standard barrel, standard steel, what they call, I think the ones with the sealed tops are called tight drums, but this is a snap lock, is what they call this kind. And they usually last a couple of years. I know people have replaced them every year, every season, in total burning.
So how much work is it to take the barrel out, put a new one?
Okay, well, what we're doing is cutting. I get two barrels, if you notice. It's only 35 inches tall. All right? Okay, 35. So our end game here is about 48 to 50. It comes up to here on me. So what we have to do is take that second barrel and cut that, and that'll be our base, and that stays in there. That one doesn't necessarily, where it wants to burn out, it's not that this won't burn out. I mean, it will eventually, but it's going to tend to burn out the top of that or around the seam more than it is down here. So this stays there. You just unclip this ring, or this ring here, unclip that and put a new barrel on it. Your base is already in there. After years, the base will have to be replaced, and then you will have to chisel out and just repeat it. But it's not all that difficult. It's not that it's something you want to do every year, but you don't have to do it every year. The solution to that is to buy a stainless steel barrel, which will last indefinitely, and of course it's a lot more expensive. But then you don't have to ever do that.
So mixed stainless steel above and regular below?
If they fit together, you can do that, but they usually don't. You'd probably want to get a stainless for both of them. Sometimes the seam on these, even among manufacturers, like a ABC company might make a slightly different roll on their edges than the XYZ company. So if you try to join them, that seal's not going to be very good. You want the seal to be real tight, because otherwise you're going to have smoke coming out of the seam here, which you don't want. And you can even seal that with a layer of that stuff.
You'll lengthen the life of your barrel by raising it 2 to 3 inches above the top of the brick or the tube coming.
Mm-hmm. Yeah.
So cooking surface close,
Yes.
but raise it.
Say cooking surface 2 inches, heating generally 3 inches, something like that, 3.5 maybe at the most. Your barrel life will lessen with a cooking surface because it's closer and it gets hotter. So I would say that's probably going to be a burnout spot. You could possibly put another stainless disc in there. I mean, if you had access to a machine shop or somebody to cut that for you, you could put a disc in there and weld it in, and then it would extend the life of it, a little bit, and you have a nice surface. But just this kind of thing is not really meant to be an expensive project. Really, we're trying to keep it to a reasonable cost. And people have definitely used old barrels, bent ones, dented, just hammer them out and just stick it on there. It doesn't look very nice, but it does the job. I used brick because it was cheaper, basically, and I had a few pieces and just got some more of the same kind. I think it's 34 bricks in this pattern. And basically, after measuring everything and establishing the footprint, set the brick on the pad, and then mixed up the mud and just made a little wall around there to keep the bricks stabilized. In this case, it can be either a builder's sand or a mason sand. A mason sand is sharp sand, and I've got examples of it out there that we'll be using, but mason sand's a finer sand than it's what they call sharp sand, and the builder's sand's going to have a little more particular in it, larger pieces, and there's going to be sharp sand in there too. But we'll have a mixture of anywhere from about 1 part clay to 2 parts sand up to 1 part clay to maybe 4 parts sand. And that really is a matter of how much sand happens to be in the clay that you have. If the clay you have already has sand in it, then you're not going to have to use as much sand to do the mix.
Dig clay out of a bank like this one out here.
Yeah, that's exactly what we did. We had a place on our 4-acre part of our farm that had some excellent clay, and I got a little bit of that. And then we had another place that they were clearing some trees, and we came upon a clay bank, and they just dug out a yard of it for me for the other stuff. It's not quite as good, but it's fine. That's what this is. Fine for our purposes.
Now the mud perlite, make sure that you put on, if you were doing the wood, you talked about that. Mm-hmm. What is the formula for that?
That's basically, you'll put in at least half perlite with half of the clay, and that might use a little bit of sand. If you don't have a lot of sand in your clay, You could put a little bit of sand in, but I'd be judicious about it, just because you want it to form, you want to be able to form it. And the perlite is mainly the insulation. The clay stabilizes that insulation. So that's basically it. And it's just you don't want it too wet that it sloughs. You know, it has to be stiff enough to form. And the water ratio, really, I can't give you a standard ratio because it really doesn't apply. You have to just add enough water to get to a consistency, which I'll show you, where you feel it's plastic. Or there's tests. You throw it up in the air 3 or 4 feet and then catch it without easing it. You know, just let it plop, and if it breaks apart, it's not right. And if it's too stiff, it doesn't really form into a ball, so you know that. I mean, you'll have to just feel it. You know, I can explain that. Anybody who's mixed cement or sackcrete or anything, you sort of understand there's a place at which you can tell that it's right, even if you've never done it. It's sort of, I don't know, it's hard to explain, but we'll see.
So there's no reason to have any kind of vent in that at any place?
But those tees have to be, those tees are clean outs, and they have to be plugged, which the plugs are, just like that, and they fit into the, you know, over the unit, so it doesn't leak. And you know, so that's the clean out areas, which is one. There could be one up here in the front, and then you know, I said we may put, you know, we have what we had over there, some other ones.
The tees as clean out areas?
Yeah, they have to be able to open them up and reach in. If there's any ash or whatever, you have to brush, because the ash will accumulate at the bends, if anything. So it's easy to get it out at that point. Let me talk about the ducts while we're on the subject of the ducts. There's a formula for determining the number of bends that you could live with and how long the pipes are going to be. So with an 8-inch duct, the starting point is going to be about 50 feet. And what we're trying to establish is how long we can make the duct work without it being constrictive, or too many bends or whatever. How many actual feet of exposure we're going to get on the duct to be able to send heat into the cob mass. So you start with the 8-inch duct. You start with a 50-foot length, and then you subtract and add depending on your situation. So every 90-degree turn is -5. So we start with 50. Every 90-degree turn is take away 5. And every T, of course, is a 90-degree turn, so you take away 5. If you should happen to have a rough pipe, which I definitely do not recommend, some people, you might scavenge a nice heavy corrugated drain, like culvert pipe, and that's really good pipe, and it's good heavy pipe. It lasts a long time, but it has a bumpy surface, which is not just on the outside, but on the inside, and that really impedes airflow. But if you happen to have a pipe like that or something with a rough inside surface, you can take away 5 to 10 feet just for that, for the roughness of the inside of the surface. On the plus side, if you have a really good exit flue like this is, you can add 10, 5 or 10, depending on how good. And this is a really good one, so I might even add up to 10 for that. So basically what you're doing is starting with 50. If you have 5 elbows, so that's 25, so you're down to 25 feet now. If you have a good flue, let's say you add 5, so now you're at 30. And if you have a rough surface inside, then you take away 5, and you're back down to 25. So we're here only at about 18, maybe 20. Not as much as I'd like to, but this is sort of what I'm stuck with. I can't really do any more without coming out.
You can't go to the wall and come up at that gradual angles. And in other words, you got what, maybe 5 feet there, or maybe 10 feet, and then go back that way, that'd be another 6 feet.
You can come up higher, you can do that, but I didn't want, I wanted the
gradual slope.
Yeah, and I wanted the bench I wanted to have the bench height at a reasonable height. I didn't want the bench up here. You know, I want the bench down here, so that left me with one level of piping. If I could have put another level and another bend, it would have worked, but it would have made the bench. I don't want that pipe exposed, so I want that would make the bench like really high, and it wouldn't be a bench anymore. It would just be a block, you know. So
it's not going. If you were to put it back to it and have the bench, what is that? Maybe This says you have here 5 feet.
5 feet, yeah, it's 5 feet here.
And if you put a foot, that'd still give you a 4-foot bench, wouldn't it?
Where do you say the back of the bench would be?
Well, the back of the bench is.
It's back here, okay.
Okay, but you've got maybe 4 foot.
Yeah,
And then you come up the wall, maybe to below the electrical thing, and have a pipe do it.
yeah, okay, I could do that, but I also didn't want too much of a depth here because I wanted a little more space between the barrel. You know, I didn't want to get too close. And that would be a good solution. And that wouldn't have been wrong to add another 5 feet and have it come up at this level and cover it with a thick bench. You know, yes, I don't want to be negative about that. That would work. I just didn't. That wasn't the design I wanted. So you get, you get another 5 or 6 feet that way. That would be okay. So anyway, it's important that this is level. This floor I had assumed was level, and I knew, but then I realized it's not level because you've got a drain there, and so all these four slabs are going into, so a slight pitch going into that drain. So we're cocked a little bit. The best way to do this is to put around, at this point, before you put the brick down, put around a layer of paving bricks or cement brick or concrete block or something, a cap block. Put a wall around here and then put a layer of sand, maybe only an inch or so, but of sand, and then screed that or flatten it, make it perfectly flat. So the floor might go like that, but the sand is going to be flat. So at one end of the sand pile, it's going to be, say, an inch. At the other end, it's only going to be 3/4 of an inch. But you can then make that surface totally flat, and you set the brick in there, and then that also gives you the benefit of being able to level it with a little mallet. You can take and level each individual brick so that the whole surface is absolutely flat, because when you want to go to put that unit on here, you want everything flat. I didn't do that. It's not the end of the world. I mean, I didn't do that. We're going to put some sand in here to sort of level things out, because the sand is really going to fill the cracks and keep the brick from moving. But I'm not going to put a bed of sand on here, because that's not how you do it. If the bed's going to be in, it's going to be underneath. But what I am going to do is then use the mortar to every course of block and every laying of block and make sure everything's level. And we'll use the mortar to do that. This kind of mud mortar is not like brick mortar in a building. It's not like the 5/8 inch mortar joint. It's a thin, certainly no more than 1/4 of an inch at each crack. 1/8 of an inch minimum, 1/8 to 1/4. So we can just use that to make things level and work it on its way up. So that's basically how, either way is fine. It's probably easier to do the sand bed, but that's not what I did. So we'll just do it this way. So what I want to do is get some sand, and we'll pour it on here and just start filling in the cracks for that. So we can go out here for this, and you probably come out here and I'll show you the difference between the sand.